All right, so in the last video, I just want to all right. In the last video, I just want to do some examples on the dual group. So a lot of these examples come from classical harmonic analysis, and you're quite familiar with them. So let's get started. So suppose your group is G is equals to the integers, okay? Well then, because it's all the integers is generated by 1, so if you have a phi inside the G hat, well, integer, by the way, has a discrete topology, of course. All right, so this is going to be uniquely determined by the generator, uniquely determined by this generator, which is phi of 1, which has to be inside the unit circle. It can be anything. Because once you decide phi of 1, then for every n inside the integer, you have phi n is just phi 1 to the n, and can be positive or negative, and that defines a homomorphism. Okay, so that essentially just tells you the G hat is just basically the same. You can identify it as the G1, phi 1, which is the same as the unit circle. And each of these phi 1 will give you a continuous map because, well, you have a discrete topology on phi, so there's nothing special here. All right, the second is that suppose I give you G is equals to the reals, okay? Then, well, if you think about what happens when you have a phi inside the G hat, well, the phi of 0, because it's a homomorphism, so it has to map the identity to identity. So phi of 0 has to be equal to 1, okay? That has to be the case. And also you have phi is continuous, okay? So because of that, well, you can have that because your phi is continuous, so it's going to be near 0 on some small neighborhood around 0. So there exists some a so that the integral between 0 to a of your phi of t dt, okay, that's going to be equals to something non-zero, okay? So it's close enough, you're integrating something close to 1, so you're never getting 0. But let's do this trick again. So we translate this integral, this fixed integral by some phi of x, okay? So here's phi t dt. So what we can do is we move the phi of x inside, so this is now integrate the x times t dt, okay? And another way of doing this x times t dt, or this I should say plus because I'm doing it on the real, so here is x plus t dt. And because we're doing it on the real, this is just an integral on the real line, we do the translation, okay? So you replace t by x plus t, or minus x plus t. So what you have is that you integrate phi t dt, you do the translation. So the lower bound now becomes x plus 0 plus, 0 plus x, okay? So you start with x. And the upper bound becomes a plus x, okay? So they have to be the same. All right, so now you show that, well, basically your phi x, when you multiply by some non-zero constant, that's equals to a integral of this form. So you can observe by the fundamental theorem of calculus, you're integrating some continuous function, upper and lower bound, they're continuous on x. So your phi is going to be differentiable, okay? So we have phi is differentiable. And because it's differentiable, now let's take the derivative. So let's take derivative d over dx. So on the left-hand side, what you have is the following. So you have a phi prime of x multiplied by this constant integrate from 0 to a of phi t dt. And on the right-hand side, what you have is that by the fundamental theorem calculus, you have a phi of a plus x and you minus the phi x, okay? And now because your phi is here is a character, so the phi of a plus x is just phi a times phi x, so you can pull out the phi x here, multiply by phi a minus 1, okay? The point here is that the phi a minus 1 is going to be constant, the integral is going to be a constant, so those are constant, and in particular this integral is non-zero. So what you have is phi prime of x is equals to some constant times phi x, okay? And your phi is a differentiable function. You can solve a ordinary differential equation. So that just implies that there exists some constant, let's say exists some constant c. You should all know how to solve this. Phi x is essentially just equals to e to the some c times x, all right? Well, what is this constant? Well, it has to be mapped into the unit circle. So because your phi x norm is going to be equals to 1, so I might as well just pretend the c is I times some 2 pi I or some other constant. Okay, so I can just pretend phi of x is just equals to e to the 2 pi I times c times x. Okay, so you can do that. And this is, well, this c here can be any real number, okay? So this little c is just a constant in the real. So every different c will give you a different character, okay? So algebraically, you will say that the dual group is just isomorphic to the real. But how about the topology on this dual group? Well, we saw that the topology is generated by those compact open sets. In particular, if I consider these kind of sets from negative n to n and let's say some epsilon, okay, that's by definition that contains only character where I have the phi of x minus 1, okay, that's going to be less than epsilon, okay, and if I just write out this phi of x is given by some c e to the I, let's just say cx, okay, so phi is equals to phi x equals to e to the I cx, okay, for some c, okay, so that's less than epsilon, okay, and well, think about what kind of c. Well, here the x is fixed inside between the negative n to n, okay, I should say for all x inside negative n to n, okay, and because of this x is 6, you can now solve the c, okay? So if you just draw a picture, so you're essentially, what you end up with is some kind of interval around this point, okay? So what you end up is some c0, c0, okay? Some kind of this open neighborhood. And you know there are neighborhood base for around the identity for the topology on the real line. Okay, so what you can do is now you show the topology on the dual group is the same as the usual topology. Okay, so this isomorphism, the dual group, is no longer purely algebraic. It's actually just the same. Okay, the topology also match. All right. Well, in particular, if you want to restrict yourself to the unit circle, so let's just say the third one. So for the unit circle, you treat the unit circle as the real modulo the integer. So essentially, you have to require that phi inside the t hat means phi of 1 has, well, it's dual group inside R, but it has to map the 1 to 1 again. So in other words, this phi of x is equals to e to the 2 pi I c, but c has to be inside be an integer because it maps each integer to 1. Okay, so you can convince yourself in that case the the unit circle, the dual group of the unit circle is just the set of all integers. Okay, that's is exactly what you have in the classical harmonic analysis, okay? And lastly, I want to do a little bit on the finite groups, okay? Suppose you have a, say, zk, okay, which is just generated by 1, okay, modulo k. Well, then the phi 1 of, well, first of all, this is a discrete group, so I don't need to worry too much about the topology. So phi 1, because it has to be inside the unit circle, and then phi 1 has the kth power has to be equals to 1. Well, that just means the phi 1 has to be equals to e to the 2 pi I over k times some power, let's say c, okay? And you can say that for every c between 0 to k minus 1, you basically have a different character. And that's essentially just zk again, okay? So you can convince yourself zk hat the dual group of a finite cyclic group is zk as well. And as an immediate corollary, what you can say is that if your G is finite abelian, then automatically you have the dual group of G is just equal to G. Okay, so that's come from an easy fact of the group theory. So if your G is finitely generated abelian, well, here is finite abelian, then you have your G is just a product of a bunch of Z of some pi to some power, okay, say ni, okay, but in any case, it's finite, so we don't really care whether it's prime or not. But because of that, well, the G hat, well, we show the dual group of a direct product is the direct product of the dual group. Let me just replace by Ki here. So this is the product of the Z of Ki, and each of these finite group, the dual is itself, so Z of Ki again, and I have that's equal to the G. Okay, everything has discrete topology, so I have this case. Well, finally, I just want to briefly mention what happens when you're taking an infinite copy of the infinite product. Okay, so we saw that when you take finite product, then the character is essentially just the product of the character. All right, but when you take infinitely copy, well, if you try to do the same thing, you multiply infinitely many characters. Now, there's no hope that this infinite product will converge unless you know most of them are equals to the identity, basically. All right. So let's define the following. So let's suppose I have maybe uncountably many. So let's say H alpha inside some index set. They're just groups. Let's define the direct sum of these H alpha. Okay, it's going to be all the H alpha where all of them are going to be equals to the identity. Let's use E alpha as the identity. Well, of course, except finitely many of alpha. Okay, finitely many alpha. Okay, so let's just basically, it looks like a direct product, but it's a much smaller group. Okay, so as you can see now, you know a lot of them are going to be identity. You can now take the product. Okay, so apparently this is a group. Okay, you take two elements, you do the usual pointwise multiplication, inverse, and so on. You can show it's closed and it's a group. It's fairly trivial. So here is the proposition. So suppose I have some G alpha locally compact abelian, and I should require all of them to actually be compact. Okay. All right, then if I consider, well, the reason I require all of them to be compact is because, well, otherwise this product group may not be very well defined. So if I consider their direct product, so here I should say G alpha inside lambda, okay? So if I only have locally compact instead of compact, then the topology on this infinite product is going to be really weird, okay? I may not even have a locally compact topology on this product. So that's why I require each copy of G alpha to be compact. So by the Tikhonov theorem, you know this is their infinite product is again a compact space, okay? So you can put a locally compact topology on this infinite product. Well, then the goal is to show that the dual group of this G is going to be isomorphic to the direct sum of these G alpha hat. Okay, so that's our goal. All right, so now let's prove this fact. Okay, so essentially we have the same logic. So if you take everything inside the direct sum of the G alpha hat, okay, so let's say you have some little, I should say phi of alpha, okay, some phi of alpha inside this group. All right, so you can always map it to phi tilde that maps the G alpha to be the product of phi alpha G alpha, because most of these phi alpha are going to be identity anyways. This product is just a finite product, so this is going to map into something inside the G hat. Okay, in other words, you have the inclusion, the direct sum of these dual groups is going to be contained in a dual of G, okay? So you for the other direction, well, for every let's say phi tilde inside the G hat, you do the same trick, okay? You let phi alpha to be phi of basically everything is E, but you just put a G alpha if you want to evaluate a G alpha, okay? You put E elsewhere, okay? This is not a sequence, I'm just showing on the alpha component, you put a G alpha, and everywhere else you put the identity. It's fairly clear to see that each of these phi alpha is going to be inside the corresponding dual group. Okay, that's going to be inside G alpha dual. Okay. Well, essentially, I just need to show most of them are just identity, except finitely many of them. All right. So how do I show that? Well, let's say for every let's pick an open neighborhood of the identity. So identity inside V contained in G, that's open, okay? Then I can think about what happens when the phi of x minus 1 is less than, let's say, 1 or some small epsilon, basically. Okay, that's for all x inside V. Okay, because you have a product topology, so there has to exist some product of V alpha where each V alpha is well, most of them are going to be equals to G alpha except finitely many of these alpha. Okay, so except finitely many alpha. And this is going to be contained in your open set V. Okay, that's the basic open neighborhood of the product topology. Okay. All right, so basically on these kind of infinite products, okay, so you have your phi x minus 1 has to be less than 1, okay? So now if I consider V alpha, whenever V alpha is equals to the entire G alpha, okay, well, if I want to find the image of phi of this V, well, of course, it has to contain phi of this infinite product, okay, pi of V alpha. And you can convince yourself because everything is centered around the identity-ish. Okay, so this is going to contain the phi alpha of G alpha, okay, or V alpha if you like, okay. So in other words, this phi alpha, the image of G alpha under the alpha phi alpha, all right, that's going to be contained in all the basically satisfy this condition. So all the z where z minus 1 is going to be less than 1, okay? And if you look at the complex plane, what it is essentially just this little bit of the arc, okay? And you know that this is a group, and this has to be contained in there. So, well, if you look at it, well, there's only one group that satisfies this. It's basically the trivial one, okay? So that implies the phi alpha of G alpha is just going to be equal to the identity, okay, or the, let's say, identity alpha. All right, so that basically just shows that the phi alpha is equals to the identity character on G alpha. Well, this is true for except for finitely many alpha. Okay, so we prove that the phi alpha is in the direct sum. Okay, this kind of finish the proof.